Right. Okay, so I think I'm ready to go, but Tsevi has disappeared. Okay, so anyway, let's wait for Tsevi to come back, but I can start the introduction here. So welcome again to our next Warsaw University Tuesday seminars. I have some background somewhere, maybe not. Okay, and today we have a speaker, Professor Tsevi Mazeh from Tel Aviv University, with his large group of collaborators. Tsevi is a long friend of mine. We worked together when I was still a PhD student in Tel Aviv, visiting there. And Tsevi is well known for his work on eclipsing binaries, ellipsoidal variables, planetary transits. So he helped a lot in all the important discoveries made recently, which led to some planetary discoveries, but also led to black hole discoveries. And Tsevi was one of the authors of the discovery of Gaia black holes recently, and he kindly agreed to give us a review about this. So Tsevi, it's a pity you're not here physically, but still, we are very glad to have you with us. Tsevi, the floor is yours.
Okay, thank you, Lukasz, very much. And first of all, Dzień dobry to all of you. And yeah, I met Lukasz last week, and he said, well, how about giving a talk in Warsaw? And I said, of course, I would be very honored. But he said, oh, wow, it's next week. It has to be with you. All right. So I said, fine. Okay. So again, thank you for the opportunity. And last time I was in Warsaw with Simchon and gave a talk on black holes. In fact, on searching for black holes. But now we have found not in the venue that we thought, but still. Okay. So. Why it's not moving? Okay, so this is my outline of the talk, and I'll start with Cygnus 61, which was discovered in '64, about almost 60 years ago, and it was a black hole, although at the beginning there was an argument about this, but finally people agreed that there is no doubt about this, about the black hole in Cygnus X1. And the idea is that it's in a binary system. The black hole sits in a closed binary, very short period, a few days, and the optical star is expanding and transfers mass onto the black hole, and this material along its way getting very hot and emits X-rays. And in fact, it was discovered as almost the first source of X-ray when people sent balloons above the atmosphere. Right. Why does it? Wow. Okay, so the common wisdom about the formation of these X-ray binaries is that there was a binary, one star filled its Roche lobe, as in this stage appears here, and then after a while, there was a supernova, and then the black hole was formed. And at the end, after a long time, as you can see below, the other star starts to fill its Roche lobe and starts to becomes an X-ray binary. But this stage here is very long, when the black hole is sitting and waiting for the other star to expand and start to transfer mass, and then the black hole could generate X-ray. And I want to call your attention to the fact that this stage of what I call compact dormant companion is very long relative to the other one. It's a few gigayears. So the conclusion from that is that for every binary, every black hole that we find in a binary, there are many more black holes that are waiting in binaries, waiting for the companion to expand and start to generate X-rays. So that's why we think that there is a huge population of dormant black holes in binaries. This is the common wisdom about what's going on in a black hole in X-ray binaries, and yeah, there is an accretion disk and X-ray emission. And this is a summary of what is almost complete. What are the known black holes that we know for now, the X-ray binaries? So you can see that the period is short, 1 day, 10 days, and the mass of the black hole is with many of them is with quite large uncertainties. Okay, so this is the situation right now, I think, and people started to search for black hole by spectroscopy, but there are many problems with identifying black holes by spectroscopic orbit of the companion. And I don't want to get into this, but we don't know very well the mass of the optical companion, and we don't know the inclination. I'll come to that. So the solution is, of course, astrometry. In astrometry, you know much more than in spectroscopy. So the idea is the following. This is the astrometric motion of a star. And you have to remove the proper motion, you have to move the parallax, and then what is left is this orbit. And from this orbit, you can conclude that it's in a binary, and you can learn a lot about the binary. And this is the issue. So people say, Gaia will observe billions of stars with astrometry, so Gaia must find many astrometric binaries, including many black holes. And there were a few theoretical papers about how many black holes in binaries Gaia will find. The problem is that they differ by 4 orders of magnitude, which is a little bit too large even for theoretical astrophysics. So it's better to find them than predict how many we will find. Okay, so then I will move now to the AMRF. This is an algorithm or a quantity that we invented in order to analyze Gaia. And the idea is the following. When you have an astrometric orbit, so you can construct what we call the astrometric mass ratio function, the AMRF. This is composed of known quantities of a binary. You have an astrometric binary, you calculate, you derive the A. Now, to connect the A to astrophysical quantities, it's very simple. The A is a ratio, is a function of Q, of the mass ratio. And if you know the mass of the primary, then by knowing A, you can derive Q, and can you derive the mass of the unseen companion. The problem is there is this factor which depends on the luminosity ratio of the 2 stars. If I2, which is the brightness of the unseen companion, is 0, then all this factor is 0 and there is no problem. But if it's not, and we don't know if it is what it is, then there is this dilution factor, and you cannot derive Q from A. That's the problem, which is a well-known problem in astrometric binaries. So what we did, we claim that we can forward modeling the AMRF and calculate what should be the AMRF as a function of the mass ratio for different cases of the secondary. So for example, if the secondary is the main sequence, then the AMRF is going to be like this. And if it is the secondary is composed of 2 stars, it can be up to this curve here. So in short, what we claim is that if we calculate A, and it is above a certain value, there is no possibility that the other star is a main sequence star. And therefore, if it is a normal star, a normal binary, it cannot be a normal main sequence, and therefore it must be a compact object. That's the whole story. It took a lot of calculation, but anyway, that's the idea. If A is larger than a certain value, which depends on your model and all kind of things, then you know it is the companion is compact object. There is no other possibility. That's the idea that we published already in 2019. And then came, of course, Gaia DR3. And DR3, that data release 3 was released in June last year. It is amazing that the release includes 1.8 billion sources. I know that for the Holl people, large number of photometric measurement is not a big deal, but still 1.8 billion is a large number. And they have a measurement for astrometry, and that's the main thing, because Gaia main goal was astrometry. But along the way, the Gaia released binaries of all kinds of spectroscopic binaries and eclipsing binaries, and it makes a revolution for all the people who work in binaries. I remember that I worked with Dave Latham, so at the beginning we published orbits, spectroscopic orbits of 1 star, 2 star. Then we made a revolution. We published 40 orbits in one paper, but that was huge. But here you have almost 200,000 orbits. But that's not the subject of my talk, but rather the orbital, the astrometric binary. So here is the CMB of the astrometric orbit, and this is the spectroscopic orbit, so you can see very well the main sequence, and this is the red clump, and the giants. Right, okay. So there is really a lot of things that one can learn about this, and I'm working now with a group about the circularization theory, or the evidence for circularization. Fantastic treasures here. But I want to focus now on what we did as we planned in 2019 to look in the astrometric binaries and identify the ones which have a compact companion. So this is a paper that we published quickly after the release. And basically that's the calculation that we did. Everything above the upper curve must be a compact object. You can see here 2 stripes. One is the location of the white dwarf, and one is the location of the above one. The upper one is the location of neutron stars. And indeed, that's what we found. This is the theory, and this is now what we derived from DR3. And you can see that there are many white dwarf binaries with white dwarf, and even many binaries with neutron stars, but that's not the subject here. So yeah, but in fact, I didn't show you the whole scale, but here is the scale of the whole thing, and you can see that there are a few systems that are well above the limit, with huge A, and that means that the companion must be quite large. Cannot be a main sequence, but must be very large star. So basically this is it. Now, the question was, are all the orbits of Gaia, are they correct or not? Because in the release, Gaia decided, against my feeling, against my suggestion, Gaia decided not to release the data itself, the data themselves, only the orbit. So one cannot judge for himself whether he trusts the orbit or not. So, and there are some problems. It's a wonderful data set, a wonderful orbits, but some of them are wrong. So if we want to focus on black holes, we have to confirm by ground-based observations, we have to confirm the orbits of Gaia. That's it. If we could confirm that without this ground-based observation, this is it. This is done. We discovered black holes. So that's what we had to do. So the first one, we published 2 of them, led by Karim El-Badry, who is a locomotive that generated a lot of radial velocity from ground-based. Fantastic to follow that. So here is the first one. This is its location. It's on the main sequence, no problem. You can see here evolutionary tracks. It is about one solar mass, and what important, 1 solar radii, this star, the optical star. And it turned out that there are 2 Lamost measurements that were performed a long time before Gaia, and before these days. But then Karim managed to follow the star since the DR3, since the release in June, with many radial velocities, and the lines here, the many green or greenish orbits is what is allowed by the orbit, astrometric orbit of Gaia. And this is a zoom on it, and you can see that they fit, the measurement fits very well, and this is the confirmation. No doubt, this is a confirmation of the Gaia astrometric orbit by radial velocity from the ground. And this is now folded with the period, and there's no doubt. There's no doubt this is a real orbit with tens of sigma. So okay, now what can we say about the secondary? The secondary, if we had only the spectroscopic orbit, then the mass of the unseen companion could be along this way, along this curve. No? Yeah, right. And the minimum mass, if we had only the spectroscopic binary, would be only 5 solar mass, which is, it's still black hole, but not. You can argue about this. But because we know the astrometric inclination, we know the inclination of the binary, which is constrained here by the Gaia, then we know that the mass of the unseen companion is 10 solar mass. So that closes everything. This is it. So here are some details about the optical star, about the companion and the orbit, and you can see this. I want to emphasize this, that we know the inclination from the astrometry of Gaia, and the mass of the unseen companion is about 10 solar mass. So this is the SED, the spectral energy distribution of the star, and it fits perfectly well with one solar mass. So it's always that you have to worry about the companion. Are you sure it's not some star, some normal star? So here you see that there is if the companion would be 10 solar masses, it will be much brighter than this one. So we would see it. So is there another star in the system? This shows us that no way, because otherwise it would be very luminous in the blue, and we don't see any hint to this. So this is it. This is the Gaia BH1. And also we have a beautiful spectrum, and there's no question that this is a normal solar type star. Anyway, so we go to number 2, and here we have a problem, a little bit of a problem, because the star is not sitting on the main sequence, but it is up, I would say, a giant or subgiant or something. It almost reached the red clump here, and this is a evolutionary tracks of the star, including the temperature and radius, and you can see the red clump is up here. It didn't reach the red clump yet, and the radius of the star is 8 solar radii. So this is a problem, a little bit problem. I will explain in a minute. But anyway, and at the beginning, we ignored all the ones that were not on the main sequence, which was a mistake, because we still can discover black holes for stars which are not giant at the tip, but subgiant like this we can. Okay, so again, this is the radial velocity that Karim managed to obtain. This is the possible orbits by the constraint of Gaia, and you can see zoom in here. The last measurement was 10 days ago. That's eight days. And it's fantastic. It fits very well, and you can see here it sits on the orbit. There's no question. It's a fantastic measurement. So what I want to emphasize is that the radial velocity, because of the huge mass of the companion, the radial velocity is not small. You know, if I worked on binaries many years ago, but an amplitude of peak to peak of 50 kilometers per second is a huge range. So there's no problem really to get these velocities. And the fact that they sit here so nicely on the graph is because the range, the amplitude is so large. Anyway, what you get from here is the same thing. From the radial velocity alone, you would say that the mass of the companion, of the unseen companion, can be anywhere here, including, of course, including the minimum mass, which is only 2.5. That means that if we had only the spectroscopic orbit, we could say that the minimum mass of the unseen companion is 2.5 solar mass, but not more than that. But because we do have the inclination from Gaia, so we know that the star, the unseen companion, is 10 solar masses. So this is it. Now the question is, so yeah, before that, these are the details about the primary and about the secondary, and you see again that the inclination is quite low, and that the mass of the unseen companion is about 9 solar mass. Now here it's a little bit more tricky, because here this is the SED, spectral energy distribution of what we observe. And now we know that this is 9 solar radii. So the question is, can another star, a main sequence of 9 solar mass, hide in the flare of this subgiant? So maybe it's not a black hole, maybe it is a normal star. So I just want to convince you, that there is no way. So first of all, if we assume that the secondary is a main sequence with 8 solar masses, its spectral energy distribution should be like this. And all this would be hidden by the luminosity of the companion, if it would were a main sequence star. Well, maybe we can think what would happen if you would have only the orbit of the spectroscopy, the radiosity. No way, because then still we should see much more light, much more brightness in the UV in the blue. And even two stars is divide this into two, still it should be more light here. So in any case, there is no possibility that the companion is a normal star, and can, because otherwise we would see it, and we don't. Okay, so that's it. I think, I hope I convinced you with the fact that we have here two black holes. And now the question is, how did they form? So, I have to go to the theoreticians that calculate these things, which I have my own doubts whether I can trust this or not, because I think these evolutionary tracks of binaries, there is a lot of assumptions there. So what people say is the usual track to generate, let's say, sinus X1 is by common envelope. The first star, the first two stars, the first stage is the more massive star, expands, and if it expands, it reaches the other star, and there is a common envelope, and through this common envelope, the binary is shrinking very quickly. And that's why sinus X1, we find it with a 5-day period. So now with us, with these two new ones, this is not 5 days. The one of them is 180 days. The other one is close to 1,000 days. So what do we do with this? How can a binary in the first stage of common envelope could escape the shrinking of the binary? This is a real problem for the people who do believe in the evolution of binaries, which I don't. I'm not part of this part. Anyway, but people are bothered with it, and because they, in effect, they didn't expect such binaries to exist, because if the black hole is there, so the progenitor of the black hole must have gone through a giant phase, the giant phase. It should engulf the other star and generate a common envelope for the binary and then shrink the binary. But anyway, people are bothered by this, but I listed here a few other options. And to me, the most appealing option is that it was originally a hierarchical triple. So the black hole was a closed binary of two massive stars, and the one that we see now, it was a distant third companion, and the binary evolved and generated, evolved and merged into one black hole that we see now. So the triple turned into a binary because the closed pair merged and generated a black hole. But one has to work on the evolution, and I hope that these two systems will provide the theoreticians with some work. Anyway, I want to show you some overall view of what we know now, and I think it's interesting. So I have three graphs about the population, so-called the population of the black holes in binaries. You know that in astronomy, 3 or 4 stars is a group, but more than 10 is a population, of course. So this is the population of black holes environment. So these are the known ones, the X-ray binaries, and there are some new ones or claim that they are dormant, but here is Gaia black hole 1 and Gaia black hole 2. So first of all, you can see that in the period they are much longer than all the ones. This is on a log scale. So between here and here, there are 3 orders of magnitude. So it's a huge difference. But what surprises me, at least, that the masses of all of them are very similar, except maybe these 2. Most of them are with a mass of 9-10 solar masses. And this is in contrast to the masses of neutron stars, which can be 1.4, 2, maybe 2.5 at most, but not more than that. So from this figure, there is a big gap in mass between neutron stars and black holes, although the gravitation wave people, they claim that they find in this gap, they find many other objects. But for us, this is what we have here, which I think is interesting. And I want to call your attention to the uncertainties. The uncertainties here are quite small relative to this one. And this is because of the astrometry. The astrometry of Gaia, the perfect astrometric orbit of Gaia, give you very well inclination. And the combination of the inclination of Gaia and the radial velocity that Karim generated, which is perfect to these cases, the combination of these 2 give you very well constrained masses for the two objects. Okay, so this is one. I have 2 more. This one I think is also interesting. This is the distance as a function of the period. So the period is still the same, but the distance you can see. This tells to me a lot that all the X-ray binaries, they are, at a distance of, I would say, 8 kiloparsecs. And Gaia BH1, we know very well, again from Gaia, is 1 kiloparsec or less, half a kilo. And Gaia BH2 is a little bit more than 1 kilo. So that tells me, at least, that those are, it's only 2, it's a statistics of 2, that those are much more frequent than those here, because in order to find the X-ray binaries, we have to go to 8 kiloparsec. But in our little neighborhood, I would say only 1 kiloparsec or half a kiloparsec. We already find two of them. Now, I want to say that these are what we discovered right now by DR3, by data release 3 of Gaia. We expect to have many more, because right now the data is based only on 36 months. And Gaia already has double the time. So in the next release, which will happen, I don't know, in 2 years or something, we will have the time span of the data twice. So it's twice as many measurements and twice longer. So we can explore the period range, which is even longer than 1,000 days. And because we will have many more measurements, we'll be able to detect fainter signal, fainter binaries with fainter astrometric signal. And I want to say something about that. As you notice, these 2 binaries, they have low inclination. And in astrometry, the lower the inclination, the easier is to detect it. Because if it is a inclination 0, you have two-dimensional motion, astrometric motion. If it is 90 degrees, then there is only one dimension of astrometric motion. So this is from that point of view, from the inclination point of view, it is the easiest. It is the easiest cases. So I expect we will have many more. Okay, and this is the last one on this. And this is as a function of the magnitude of the brightness, of the optical brightness of the companion. So you can see that these are very, very faint stars, because the secondary is K star and G star, and they are far away. So therefore, these are faint. But of course, the first one to be detected was Cygnus X1, and Gaia BH1 and BH2 are bright. So there's no problem in follow-up with radial velocity. And Gaia can detect astrometric binaries up to, I don't know, 18 magnitude, so there's no problem. But for follow-up, they are bright. Yeah, they are really bright. Right, and this is discovered 59 years ago, and these are now, this gap is almost 60 years. Okay. So this is enough for Gaia BH1 and BH2. I think I have another few minutes, so I want to show you another two topics just very shortly. So we also discovered by this AMRF, we discovered many other compact companions, and they are plotted here. And one of them, I just want to focus on one of them just as an example. This is, we believe, a neutron star, which is here in the AMRF, and this is here in the eccentricity versus period. And in fact, there is a radial velocity confirmation of this as well. Here is the orbit that we published in the binary, in the Gaia binary paper. And we did release the astrometric measurement, which is an exception. And radial velocity, and the companion is 1.5. So we do have neutron stars. Don't worry. In the Gaia data, there are many neutrons, because the common envelope, the common wisdom is that there are many more neutron stars than black holes. So they are waiting there to be analyzed. And I just want to finish by saying that this is something that I work with Milena and Pavel. There is another way, and of course, Lucas, to detect binaries, and this is by ellipsoidals. If the binary is very close, the binary is a short system, then the binary rotates, and then we can detect the ellipsoidal. I don't need to tell the Ogle people about ellipsoidals, they know better than me. So we published about 6,000 short period Gaia ellipsoidals that we think that might have a compact companion, either a neutron star or some of them may be black holes. And today, I think we got a positive response from the SOL, from South Africa Large Telescope, and we have time to follow a few of them. So maybe we will find more neutron stars from Gaia, but through this ellipsoidal channel. So for all of them, we need to follow up. So yeah, so I think I will end by that. Thank you very much.
Thank you very much. Thank you, Tzvi. Questions from the audience first. Nada.
Thank you so much for this.
Should I stop sharing the screen?
No, that's okay. Well, That's fine.
Okay. Now I want to see the people.
Yeah, thank you so much for this talk. It really was great. So I was just wondering, I think you were showing the AMRF graphs for the both black holes that you discovered, which were really far away in the mass of the black holes and in the A. I guess
I'm not sure I'm hearing you well. Can you speak close?
I'm sorry. Okay. So you were showing when you were showing the two outlines, which turned out to be the black hole 1 and black hole 2.
No. These two. One of them is not a true orbit. Sorry that I interrupt you. One of them is BH1. The AMRF of the second one I didn't show.
Okay, yeah. So because my question was because I believe there were at least 4 that were also really of the line where you said that there were anomalies. I don't know how else to call them. So I was wondering if you did the study what they were, but yeah.
Yeah. Well, you have a sharp eye. I must say. We followed them and they were wrong. They were wrong orbits. They were fake.
Okay.
That's why it is essential in this stage. I hope it will not be the same with the next release of Gaia, but right now, every orbit that we find interesting, we have to follow it by radial velocity in order to confirm it.
Okay. Yes. Thank you.
Good for you. Good for your eyes.
Well, I just will continue on this topic a little bit because you said that the face-on orbits, right?
Yes.
Most easy to find in astrometry, but this is completely contrary, opposite for radial velocities, right?
Exactly.
So how do you combine? You might end up having, a nice astrometric orbit and no RV signal. What do you do with that?
I cannot help it. If it is exactly 90 degrees, if it is exactly 0 degrees, then there will be no spectroscopic signal. But 0 degrees, very, very rare, because the probability, the random probability for having an orbit with 0 inclination is really, really small. So it is interesting, and I don't think many people are aware of this. I want to repeat this. If you have astrometric orbit, and this is the plane on the sky. If it is a 0 degree, then you can see by astrometry the 2 dimension of the motion. But if it is a 90 degrees, so you lose from astrometry point of view, you lose 1 dimension. So it's basically the signal is smaller by a square root of 2.
But then radial velocity will complement it, right? So in a way, the edge-on orbits and radial velocity are better cases than the face-on and no radial velocity. Do you agree?
Yes, I agree. I definitely agree. I just note that these two have low inclination, and therefore they were easier to detect by Gaia, and that's why I expect that in the next release there would be many, many more.
Mm-hmm. Okay, great. Any more questions from here? Anyone? There is one from Zoom. Pavel?
Yes. Thank you, Tsevi, for the talk. Very nice results. I have a question about the plot with distance and period.
Okay.
For the known low mass and high mass X-ray binaries.
Yes.
And Gaia black hole 1 and 2. So my question is how the distances were calculated for that. Is it simply taken from the Gaia DR3 or maybe from the spectra?
You mean for BH1 and BH2?
For example, yes, yeah.
No, that's easy because Gaia, that's the first thing it does. It measures distances.
Okay, okay,
the parallax.
okay, yes.
For the other ones, I'm not sure if this is based on Gaia. It was calculated before because the spectrum of the optical star was identified from the spectrum, and then from the brightness they estimated the distance. The distance is quite far, so therefore it's with large uncertainty.
So my second question is, did you, well, I'm pretty sure that you did check the astrometric signal and the quality of the astrometry for these two targets from Gaia DR3.
So as I said, Gaia did not release the individual measurements, only the solution. The solution includes proper motion and parallax and the orbit, right? So it is a complicated solution, but we could not check. Although we are from Gaia, but we were not allowed to do that, to use data which was not released.
But in Gaia DR3, you can also find the astrometric flux like Ruve parameter, which is
yeah, that's true. That's true.
Yeah. So I mean this astrometric flux or the chi square.
Yeah, you mean the I don't remember what is the Ruve after you solve for the orbit. I think it's very small because the astrometric orbit of Gaia is very well constrained.
Well, yeah, I was asking about that because we found that for our microlensing events, very often Gaia parallaxes are underestimated, and we use spectroscopic distances because the astrometric signal simply is affected, and Gaia is wrong for some of the microlensing events. So I just wanted to compare the situation of our events and these two stars. I know that this is a different story, but
Pavel, what is the distance to your objects?
Well, yeah, it's farther. Yeah,
they are far, but ours, it's in our backyard. It's 1 kiloparsec, a little bit more, a little bit less. So I think the distance is
should be fine. Yeah, but it is worth to check.
Right.
These parameters. Okay, thank you.
Thank you.
So I'll just have a quick question about the extinction, right? I guess for the near black hole 1, it's negligible, but for 1 kiloparsec away, there might be a little bit of extinction, which might, dim the ultraviolet part of your SED a little bit. But have you considered that, including this?
I think we calculated that. Okay. It's not much. No, it's not. And I showed you that if the companion is 8 solar masses, it should shoot very, very orders of magnitude above what we see.
Okay, perfect. I don't see any more questions, so thank you very much, Tsevi, and let's thank our speaker.
Thank you very much.
Goodbye.
Milena, you want to talk?